Hello everyone, welcome to a pre-lab session for week 5 of FIT3143 parallel computing. So in today's pre-lab video tutorial, we will actually go through some of the MPI functions, message passing interface functions for point-to-point communication and also for collective communication and for some reduction-based operations. Before that, I will also discuss with you all um, how do we do communication between shared variables using threads, and then in a shared memory perspective, and then from there I will transition to how then we can share variables between processes using message passing interface. So at the end of today's video, we hope that you will have a clear understanding between parallel programming on shared memory using POSIX or OpenMP, as you have learned in the previous weeks, and parallel programming on distributed memory using message passing interface, which you will learn in the coming weeks ahead. All right, in today's video and also in the coming weeks ahead. Now, so I'm going to share my screen and then we will get straight into the activities for today's session, pre-lab session. Okay, so now if you look at the lab week 5 specifications in Moodle, all right, you can see that in this week's lab, we have given you about 5 questions, but the first 3 questions are guided with sample solutions for you to try out and to understand, and I will provide some explanation based on this. Whereas the last 2 questions, question 4 and question 5, requires you to complete this task based on within your respective teams. Okay, now before I go further, I would like to discuss with you all the first part here. Okay, so the first example, the first question here is merely making sure that everyone is able to run a very simple MPI, compile MPI application. So this is like the baseline to make sure everyone is able to, if everyone is running MPI, either in your, all of you are able to run MPI in your virtual machine, or if you have installed MPI into your native operating system. All right. Okay. The second one. Okay. So I will base my examples from this question. Okay. So what it says here is a common need for one process to get data from the user, either by reading from the terminal or command line arguments, and to then distribute this information to all processes. So what it's saying is that, let's say you have a process that prompts the user for a value, and then you want to then distribute the value to other processes. Okay. Now, let's say if I ask you, how do you implement this using threads? Okay, let's say let's go back to threads a bit. Right? Let's roll back a bit to POSIX threads. So let's say we have the main function. The main function prompts the user for a value, and this main function then updates a global variable, which then can be read by the threads, and the threads will then print out the updated global variables. So before I go further, let's be sure that we have a good understanding between shared memory parallelism and distributed memory. So in shared memory parallelism, all right, the main function creates the threads. Each thread will have their own stack variables. Each thread will have an internal instruction pointer that points to the compile instruction, the thread function to execute. But all of the threads can actually share the heap region of the memory. So whatever global variables or whatever heap memory they have created can be shared by the threads, and also can be shared by the main function. If you have a main function, I mean, of course you have a main function running. Okay. Now, so based on this context, how do we actually complete this particular question for threads? Now you'll be thinking, well, it's very easy. I just ask the main function for a variable, and then after that I will write the variable to a global, I write the value to a global variable, and then after that the threads will read the variables, and then it will print out the variables. Sounds very simple, but actually it's not as trivial as it looks, because in this case, to get a proper implementation, we would need to actually apply signals. We need to use condition variables to signal the thread that the global variable has been updated, and then from there, the threads will then be able to update the variables accordingly. So for that, I have prepared an example for you all. So this all of this code. So these are all the codes we're going to go through today. Okay, so it's quite a lengthy discussion over here, but I will put in some annotations later on in the video, in the YouTube video, so at least you can skip to the parts which you are interested to find out more later on. So the first one is this. Okay, so this all of the code files we provided to you all. So I will walk through the code with you all, so at least you all can understand, and then from there you all can compile the code and do further learning based on this given example over here. So again, this example is based on the specifications of question 2, but implemented not using MPI, but in POSIX threads. Okay, so here, what I'm doing, I'm just going to go through quickly with you all. Okay, maybe I can try to draw it out for you all here. Okay, here you have the main function. So this is a POSIX thread, huh? This is shared memory. Okay. Okay. So you have the main function. So you have to understand the main function is running as a process. So in a way, it's a thread by itself, but this is a main thread. So should the main function be terminated, all threads created by the main function will be terminated by the operating system kernel. Okay, so let's say you have thread 0, I call it th0, and thread 1. All right. So what the main function does, the main function will prompt user for a value. Prompt user for the value. So let's say the value is updated into a global variable g value. So then what thread 0 and thread 1 needs to do is that they need to print out the g value. Print out the g value over here. Okay. Now, based on this condition, but there's a caveat here. We only print out the value in g value variable should there be a change in this variable. We don't want to continuously print this variable, the value of this variable, when there's no changes to the variable. It will be redundant. So thread 0 and thread 1 will only print the content of g value should there be a change to the variable here every time the main function prompts the user for a value. So this operation here runs in a loop. Okay, this operation here goes in an iterative loop, and the threads here will only be triggered every time there's a change to the value over here, this variable, change to the content of this variable over here. So how do you actually realize that in threads? Now, it doesn't appear to be so simple anymore, doesn't it? Okay, so what we have to do is that every time we update the value here, let's say g value equals to, let's say we update the value inside here. What it needs to do is that after that, the main function needs to signal this thread, and then signal the second thread to then wake up. Okay, we don't need this. It needs to signal this thread. So when this thread will have a condition wait. I'm using condition variables here. This thread will here have a condition wait. So when it signals, it wakes up, and then it prints the g value. And then it wakes up, and then it prints the g value over here. So that is what the main function is supposed to do. So the main function prompts the user in every loop for a new value. The user enters a new value. For every new value updated into the variable, the main function signals the thread 0 and thread 1 who is in the condition wait status. And then when they get the signal, they will wake up, and then they will print the values. And then after that, they will continue going back into a condition wait. So this one also is running in a loop. All right. But the most important thing is, these threads will print out the value, only the value of this particular variable, only should there be a change in the content of the value. I mean, if should the user specify a value that will go into this variable over here. So this code actually attempts to implement that. So I'll quickly go through with you all the code here. So if you're not familiar with POSIX threads and you're not familiar with condition variables, please refer to my YouTube channel. So the YouTube channel here, I'll provide a link to the channel in this video later on. So you can refer to week 2, the lecture on part 2. So in part 1 and part 2, we actually cover quite a bit in depth about POSIX threads and also about the condition variables, how to use condition variables with some examples. So please refer to these videos to get a better insights on how we can use condition variables for thread signaling. Okay. So once you've seen these videos, then you will have a better understanding on the code that I'm discussing over here. All right. Okay. So what we have over here is that I've declared a mutex. So because this mutex will be used to lock this shared variable here. So this is our shared variable. Okay. This is our shared variable. So this variable will be accessed. This is considered in a way. This will be in a heap region, although it's not a pointer or anything like that, but because the global variable, this variable will be in a heap region inside here. Okay, and multiple threads can directly access the heap region in memory. Okay, I'm repeating this a few times because I need you to understand this. All right, so just hang in there for a while. Okay, now inside here. And on top of that, I've declared another 2 global variables, but this is a mutex for this to lock this variable. And then you see, I've created a condition variable, okay, a condition variable array. So this is a pthread condition underscore t. So again, guys and girls, if you're not familiar with condition variables, please refer to the lecture video, week 2 lecture video, part 1 and part 2 on POSIX threads. Okay, the link to the channel will be provided in the description of this video. So inside here, I've created an array of condition variables based on number of threads. So here I put 4 threads. So I've created 4 condition variables in an array and initialize them to a default value. Okay. So inside here, this is standard. I created an ID for the threads to store the thread ID to store the created threads. I created an integer based array to store the unique thread IDs. Okay. Then I initialize my mutex. And then in the for loop, when I'm forking out the threads, I will initialize the condition variable. So each thread will have its own condition variable. Each thread here will have its own condition variable at location I. I is the thread ID. Okay, this thread also will have its own condition variable at location I based on the given thread ID over here. That's why I created this. I called pthread condition init. I'm passing the address of the global condition array at location the thread ID. So each thread will have their own. So if thread 0 will be here, will have their own condition variable. Thread 1 will have its own condition variable, and so forth, up to the number of threads that I specify over here. And then after that, I created the threads over here. So this is standard. Each thread will then run this function over here. So now we see this function, the thread function. So all the threads here are running the same function. Thread 0, thread 1 are all running the same function over here. And inside this thread function, what's happening? I'm getting the unique rank value. This is from the argument it passing inside here. All right. Then from there, I will call a mutex lock to lock the. So before you want to print out the value of the shared variable, you want to lock it. And then after that, you go into a condition wait. So you lock first, and then you go into condition wait. So which means you are releasing the thread is going into a suspended state while waiting for a signal from another thread or the main function in this case. So the thread will not print out anything until there is a signal from the main function telling that time for you to wake up and time for you to print out the new value in this variable over here. Okay, then you will allow the mutex. So this continues on as long as the content of this variable is larger than 0. So the first time it goes into a wait condition. It waits for a signal from the main function. Should it receive a signal, it will wake up, get the lock for this variable, okay, and then print out the value and then release the lock. So other threads who are signal can also get the lock and update and print out the updated value for their respective threads, and then unlock. And then as long as the variable is larger than 0, it will repeat the whole process again. All right. So this is how we are using the condition variables over here. Now, so these threads run as soon as you call pthread create. So the main function prompts the user for a value. So we say enter a round number over here. I say enter a value larger or equals to 0. Then here you see the main function attempts to get the lock. Now the main function can get the lock because all the threads, when the threads call condition wait, they will release the mutex to this variable. So whichever thread that was holding the mutex will release the mutex to this variable. So which means the main function can actually now acquire the lock. All right. And then the main function then prompts the user for a value, unlocks the mutex because it already updated the value, and then it signals all the threads. So here, wake up all threads. Wake up all the threads because all the threads were in suspended state when they call the condition wait. So I'll wake up each thread based on the respective condition variable in the array, and then each thread will then wake up, print out the new value, unlock, and then repeat again. All right, so that's how it works. So every time, so this kind of follows the diagram over here, although the diagram is a bit messy. All right, so every time the user enters a value which is stored inside this particular global variable, the main function will signal all the threads to wake up. All the threads will wake up and then print out the value, and then they will go back into a suspended state again. And this continues on until the user enters a value which is less than 0. And then when it's less than 0, you exit the do while loop. I mean, the threads will signal and then exit the do while loop. And then same thing here also, the threads will then, sorry, my apologies, the main function will wake up all the threads and then exit the do while loop. And then the threads will print out the updated value and also will exit the thread exit the do while loop in the thread function, and then the threads will return 0, allowing the main function to join all the threads and then conclude the program. All right, so this is the general layout here. If I were to ask you all to do this question properly in threads, this is what it would take you all to do. All right, and if I were to compile the code, okay, if I have to compile the code, so if we are using threads here, so there's no MPI CC yet. So I'll just use wall, and this is the file name, pthread signaling. All right, and then -o output file, and then I'll put LP thread. Remember, we are using threads, so we have to specify a thread library. Compile, no errors, and then we run the application. So you can see, okay, the main process starts. Each thread initially just printed out the ID just to indicate that they're running. And then now the main program is asking the user for a value. So the threads are not printing out anything. You see, the threads are not printing out the new values yet. Oh, sorry. The threads are not printing out the value of this particular variable, G value. It's not printing out anything yet. It's now in suspended state because all the threads are waiting for a signal from the main function. So when the main function enters a value, let's say I enter the value 50. Okay, 50 is larger than 0. So when I hit the return key, this value 50 will go into this particular variable. Okay, and then the main function will unlock the mutex and then wake up all the threads. So you see, when you wake up all the threads gets woken up, and each thread will print out the value inside here. And then they will go into a suspended state again. And then again, I repeat the process. Okay, the main function now gets the mutex, asks the user for a new value. So I put 100, and then it repeats again. Now, bear in mind, I've put a sleep here for 1 second, because if I don't put a sleep, in this context, for this particular example, if I don't put a sleep, what happens is that the main function will always have control of the print screen. The threads will never be able to print, and the program will not be able to work. So I'm just putting a sleep here intentionally. Okay, and also here, just to make sure that the threads can print out the values first, so that at least we can visualize how this particular example works. Okay, so if you're writing to a file, then probably you don't need to put a sleep. But this sleep here, sleep for 1 second is there. I'm just putting it so that the threads are able to also print to screen. Okay, so I continue this 80. The main function gets the value, updates the main function gets the value 80, updates the value into the global variable, and then the thread signals the threads to wake up. The threads wakes up and reads the value of the global variable. So each thread will. So the threads writing to 80 here is in sequential, but not necessarily in order. So whichever thread gets the mutex, prints out the value, and then releases the mutex. So the next thread who was woken up gets the mutex and prints out the value also. All right, it continues on like this. So I hope this example gives you a very good idea on how threads can share a global variable. And bear in mind, this global variable is in your heap region of your memory. Okay, all the variables here, like this integer pointer, this integer my rank, these variables are inside the stack. Each thread will have their own stack variables, but the threads share the global variable, the threads share the global mutex, the threads share the global condition variables. So these three variables are all inside the heap region, hence the term shared memory. So this is how you do it. Okay, so so please go through this code, and if you have any questions, you can always consult the tutors or the lecturers for this unit for further advice. Now, this works very well. So I have put 4 threads here. I can run with 6 threads, 8 threads, 10 threads. Okay, and this represents a very good communication between threads and the main function when trying to access a shared variable in memory. But as I mentioned before, the challenge here in parallel computing is that, yes, you may have multiple cores today in a computer. But what happens that if you need more cores, more CPU power, but you just don't have it in a single CPU, but you have multiple computers connected within a network, how can you expand your parallelism across a cluster network? That is where we go into parallel programming with distributed memory through a network. And that's where message passing interface comes in. So in our lecture for week 4, we've already described to you all what is the idea of parallel computing in distributed memory, whereby in a distributed memory, each process now will run independently. All right, each process will have their own heap region of memory, their own stack memory. They will not share the heap region with other processes, even though if you have multiple processes. Okay, so in shared memory, right, I'm just repeating this again because it's very important for everyone to understand. All right, if you understand, that's good. Then maybe you can skip this part. Okay, so in shared memory, so this is your memory region. Okay, so you have your CPU over here. Okay, just a very, okay. In your CPU over here, let's say I have 4 cores. Okay, I have 4 cores. So in this case, let's say I create 4 threads: TH0, TH1, TH2, and TH3. Now, in shared memory, let's say I'm using POSIX in this example, all threads are able to access the heap region of memory. They're able to access the heap region. They share a common heap region to this entire main program. So the main program, the main function is also a thread. The main function will probably occupy one of the CPUs, or probably depends. If the main function is not doing any task, then the main function will just be using up the CPUs just to govern the threads, or to gracefully destroy all the threads once the threads are joined. But all of these threads and the main function, they share a common heap region. That's why I'm always coming back to this diagram over here. All the main function and all the threads will share a common heap region over here. So you can create many threads based on the number of cores you have on your CPU processors. But now let's imagine, let's say you need more than 4 cores. Let's say you're dealing with a computationally expensive problem, a very computationally expensive problem. Okay, so you need more than 4 cores. Let's say you need 8 cores, example. So, but you have 2 computers. Okay, you have 2 computers at your dispose, all right? So you have You have two computers. Both computers have a similar architecture. You have CPU here. Okay, you have 4 cores also. Okay, so if you were to create another POSIX threads over here with 4 threads, these 4 threads cannot communicate with the other 4 threads in this computer. So let's say, let's call this as node 1, node 0. Let's call it as node 1. Okay, node 0, node 1. So how do you get both computers to communicate such that they will create a form of distributed memory? That is where we are going now. Distributed memory. And how we achieve this? This is all achieved through network. We will use your network architecture, whether local network or internet. Okay, we will use a network architecture to allow the processors. So we're no longer using threads. Okay, now we call them as processors: P0, P1, P2, P3, and then here we will run it as P4, P5, P6, P7. So now we have 8 processors. We have 8 processors within a communicator. So this is your network. Your network will be a communicator. We have 8 processors within your communicator which are working in parallel. And the memory that the processors are using are all within a distributed memory context. So for the processors to share the values of their variables to another processors, we no longer have the luxury of shared memory parallelism. The processors, let's say processor P0 wants to share its variable value to processor P4, processor P0 needs to send the value over through a network, such that processor P4 will receive this value. And the same thing applies, even though processor P0 and P1 are in the same computer, but for processor P0 to share a value to processor P1, processor P0 will also need to send the value to the network, but because processor P0 and P1 are within a local host, the value will then go back to P1 within the same localhost network. But if processor P0 sends a value to P4, P5, P6, P7, the value will traverse through the network within the communicator, and then it will reach P0, P4, P5, P6, P7. This is the essence of message passing. That's why it's called message passing, which forms the backbone of your entire distributed memory parallelism. So once you are able to exchange information, then all processors can work in parallel. And this is governed, the whole distributed memory parallelism is governed using MPI, which is your message passing interface, and we are using Open MPI. So MPI is a specification. We are using Open MPI, which actually implements the MPI specification into a library, into a C library, which we are using for this unit. That is how we are evolving from thread-based shared memory parallelism to distributed memory. So yes, in your virtual machine, you'll be using the processors within one computer. But later on, when we expose you all to Monash, you will have the opportunity to run your program across 2 nodes, 2 server nodes. Each server can have about 16 processors, 16 cores. Then you have a good exposure to a proper cluster computing for parallel computing. Okay, so this is where we're evolving now. Okay, now, so going back to the specification of the lab, so now they're asking you implement this using MPI. All right, so now I want you to re-implement all of this. How can one process get a value? So now in this case, let's say we make processor 0 as our main function. Okay, let's say we make processor 0 is as our main function. The other processors will behave like our threads in the shared memory version. So we make processor 0 the main function. So processor 0 will prompt the user for the, so we have, so let me draw it for you all here. We have processor P0, processor P1, processor P2, and so forth, until processor P7. In this example, I have 8 processors. So my process count, is 8. Example, okay? So imagine I'm using MPI run -MP8. Okay, MPI run is an open MPI application. Okay, so MPI run will run your compile program across all processes within the communicator. All right. So here, I want to make my processor 0 as my main function. In this case, it also acts as the root. Normally, we use the word root. Okay. So processor P0 will prompt the user for the value, and then it will send the value to all of the other processes within the communicator. It will send the value to all of the other processes within the communicator, and all the processes will print the value. All of the other processes will print the value. I mean, whether the main function, the main processor wants to print is optional. So that is what this question number 2 is asking you to do. But it's asking you to use broadcast. Before using broadcast is a collective communication. Let's say, how do I do this? So now, before we go into how we achieve this using MPI, let's cover the basics of MPI. So for that, we have our first code over here, MPI basic. So this is a very simple code. All right. Okay, I've provided some explanation in the lecture for last week. I mean, sorry, yeah, week 4's lecture for MPI. You can also find the video in the lecture in the YouTube channel. Now, inside here, we can see that, I mean, this one, the process name is optional. I just wanted to get the processor name. This is not compulsory. You can skip this. But the important ones is init, comma, and comsize. So MPI init initializes the communicator. So it initializes the communicator. Okay. MPI comrank gets the unique rank for each process within the communicator. MPI comsize gets the number of processes running in the entire communicator. So each process knows their unique rank. Each process also knows how many processes are there within the entire group. That is very important. Based on this information, then you can achieve data parallelism. Okay, you have done it in a similar manner for threads for your prime algorithm in the previous lab tutorial. Okay, so we will do this in a similar context for MPI for the next lab activity. All right, but this week's lab is a bit more straightforward in the sense that we're just focusing on some simple MPI activities. Okay, so we get number processor. This one is optional. This is just optional. I put it here optional. So it's not something that you need to do. It's just to get the unique process name of each process running in the in the communicator group. Okay, then I just put there hello there. I am my rank out of my number of processors, and then this is the length. So to run this, you need to use. Oops, sorry, I have to exit this. So just to go back to the earlier example again. So if I put let's say if I put 10, I'll get the values 10, 110. If I put -1, then all the threads will exit. I forgot to show the last part. I put -1 over here, but it's okay. It's a small thing. Okay. Now, so going back to the MPI program. So now to compile the MPI code, you can't use GCC anymore. You have to use MPI CC. Okay, so it's all installed in your virtual machine. If you're running MPI, if you want to run MPI as a native application in your operating system, you're not using virtual machine, then please refer to week 0 in Moodle. In week 0 in Moodle, we have provided a video here on how to download, compile, and install OpenMPI in your local Linux system. If you're using Linux as a native operating system, all right. But if you're using with the virtual machine, then shouldn't be a problem. This video is also available in the YouTube channel list. All right, I think it's available here. Yeah, week 0. Okay. Anyway, catching my breath a bit. Okay, so going back to the example over here. So with MPI CC, I just enable all warnings. The output file, I just put out here, and oh, sorry, I forgot to put the code file. So what's the code file here? MPI basic. And then the output file here. Okay, no errors. Now, to run an application using Open MPI, you just can't run it out here. It won't work. If you do that, it will run as a single application. You need to use MPI run. So remember, if you're executing or running an MPI application, you need to use the MPI run engine. The MPI run application will actually then create, will actually run multiple processes. That's why you put -MP number. The -MPA specifies number of processes. I put 6 over here because I'm using 6 logical processes in this virtual machine. And then I put the output application. So what happens is MPI run, okay, MPI run will then run this application 6 instances, okay, will run this application 6 instances across, just give me a second, okay. So MPI run will run this application 6 instances. Just give me a minute for a while. Okay, sorry about that. Okay, now, so MPI run will run this across 6 processes. So please forgive me just now for the short hiatus. Something came about. Okay, so going back to the screen over here. So we have 6 processes. All 6 processes. In this case, 8 over here. So maybe if I'll just keep it 8 over here. So MPI run will run each of this particular application. This whole application will be executed 6 times. But each process will have their rank value and their number of processes. Will have the unique rank value and number of processes. All right, so if I run this now, so I can see over here, this particular application is executed 6 times. All right, so if you have in this virtual machine, I have 6 logical processes. If I'm doing a heavy computational task, each process doing a heavy computational task based on their workload distribution using the rank and processes, then we can see all 6 processes running at maximum capacity in your CPU monitor. So the same thing like threads, but now we don't see any thread creation. We don't see any pre-threads creates or anything like that here. All right. Instead, what we are seeing is that MPI run is now governing the parallelism for us. I mean, in the sense that MPI run is now creating the multiple processes which would allow them to run in parallel, okay, within a given node or across multiple nodes. So if you want to configure MPI run to work on multiple nodes, that's a separate topic. It's not something that we'll discuss here. For now, we are using MPI run to run multiple processes within a single node, within a single computer. So just understand this for now. All right. Okay. So this is just baseline for you all to understand on how to get MPI working. So you can see each process has a unique ID and a number of processes over here. Okay. Once we have gotten this baseline cleared already, okay, the next thing now, we go back to our problem. Okay, go back to our problem. The problem says that we need to actually have one process read the value from the user and then send the value to all other users. So let's say I try doing this using a normal send receive. All right, so this is my send receive code. Okay, so in my send receive code over here, what I'm doing, so this is what we call as a point-to-point communication. Okay. Now, in a point-to-point communication over here, pay attention closely. So you have my rank equals to 0. So remember, we will run this code. This is single program. this one program will be executed multiple times. Okay. So if the rank is 0, the rank will prompt the user for a value. And you see, the rank will then call MPI send. It will send the value to all other processes within the communicator. So I'm starting from 1. You don't put 0. You don't want MPI send to send back to itself. Okay. MPI send rank 0, as you can see here, it goes back to the diagram over here. Okay. So rank 0 prompts the value from the user, and then it calls MPI send and sends the value to all other processes within the communicator, MPI convol over here. All right. So if you look at MPI send, so how do you find out what is MPI send, what is MPI receive? So this is where we would employ you all to look at the documentation. If you go to openmpi.org documentation, you can find all the information you need for all the available APIs. If you go to MPI send over here, in MPI send, it gives you the function prototype. Maybe I can zoom in a bit. So you can see over here, it takes in a pointer to a buffer. It uses a void pointer. So void pointer means generic pointer. Again, if you're new to pointers, please refer to the pre-lab week 4 videos on pointers. There's an additional tutorial on pointers there, and I hope that will give you a very good understanding of pointers and why pointers are used in functions. All right. So this send takes in a pointer to an array or an element. How many elements in this array? What is the type of element you want to send? Where you want to send this element to? The tag is just a constant to specify that this is like an integer enumerator you want to specify to each message over here. So normally by default, probably is 0. And you can use the communicator, convol. So if you look at the code over here, I'm calling MPI send, the value. So now I'm only sending one value. I'm not sending an array or a buffer or anything like that. I'm only sending one value. All right. So I'm putting in the address of this value. So you see this, it's very important to see this, guys. Each process, okay, all the way to P7, each process will have their own stack. Each process will have their own stack. Excuse me. So which means that the integer value in this process 0 and the integer value in this process 1 are different. They're not sharing. So in this case, if process 0 executes this code, process 0 checks, oh, I'm my rank 0. I prompt the value from the user. Let's say the value is 10. Process 1 and all the other processes, the value is still -1. All of them, the value is still -1. So how does process 0 inform the other processes that, please take note that the value has changed from -1 to 10, you have to use MPI send. That is the idea. In threads, like what I mentioned just now, the main function signals the threads then wake up and then get the value, and then they print out the value or do something with the value. But in MPI, in distributed memory, because each process doesn't share the heap memory, even though they're running in the same node, they won't share the heap memory. They have their own heap region. They will not share any memory with other processes, okay, whether or not in the same node or across multiple nodes in a cluster. The only way a process can update the variable of another process with the value is to use MPI send. That's why when I call MPI send, I'm sending this value, but this value is from rank 0. It's taking the content of this variable and sending it to all other processes in a for loop over here. All right. Now, the most important is this. This is parallel. This is parallel computing. So all these processes, P0, P1, P2, all the way to P7 are running in parallel. So which means while P0 is sending, when we run MPI run and execute all processes within a communicator, while P0 is calling send, P1 is waiting to receive. while, okay, receive. While P0 calls send, P1 is waiting to receive. P2 is waiting to receive. P3 is waiting to receive. So they are working in parallel. But because the send and receive are blocking based communication, which means when any process calls send, it will wait until the data has been transferred to the network buffer or until a connection has been established with the recipient over here. I is a recipient. So I1, process 2, all the way until the last process. Same thing, MPI receive is also a blocking communication. It will wait until, so I put 0 here. So you can see all the processes, there's no for loop here. Look carefully, there's no for loop. So the process P1 to P7, there's no for loop here because they're all waiting for one value from who? The root. So here MPI send, we put destination. If you go to MPI receive, over here, MPI receive takes in the following arguments. It takes in the buffer to write the variable into or the array into, how many elements to receive or how many elements to write into here, the type of the element, the source, from whom to receive, the tag, communicator, and status. Status just tell you that what is the status of the received message. Normally, if you want, you can use MPI status ignore as given in the sample code over here. All right. So the tag must be the same tag as send. So if send is just tag 0, receive must be 0. So normally we put it 0 by default. Okay. So you can see over here. So this is the receiving source where we want to receive the particular message from. Okay. Now, based on this, MPI send, MPI receive. So while the process 0 is sending, process 1 is receiving. So this happens. All of these are going in concurrent, in parallel. But because the send and receive is a blocking communication, so the send and receiving part will be serialized. So that is where MPI send and MPI receive represents an internal barrier. Okay, it's like an internal barrier. So be careful of how you use send and receive. Although send and receive is very powerful, it allows you to send messages across multiple processes within the same node or across different nodes in a cluster. But if you don't use them carefully, you can actually slow down the performance of your overall parallel computation. So we call receive over here, and then the processors will then print out the receive value over here. So now if I were to compile this code, okay, so now I'm going to run MPI. So this is MPI send receive. Okay. Compile them, no problem. I'm going to run with 6 processes. So now you can see here. So now it says rank 0. So only rank 0 is asking me for a value. Okay, only rank 0 asking me. So this is similar to the thread example, that the same requirements, but implemented using MPI now. Let's say enter value 100. So you can see all the processors. Processor 1 receives the value 100. Processor 2, 100, 3, 4, and 5. The order is not the same. Okay, and then it says again enter a round number. So don't worry too much about the printing order. It's just a behavior MPI. So now it's waiting for me to enter a new value. So can you see processor 0 gets the value from the user and then sends the value to all other users in the communicators. All other users now share the same value, share the same content in this VAL variable. I enter another value, that happens. So it's exactly the same implementation with, not same, sorry, my apologies. It's the same behavior as the p-thread signaling, but instead of using POSIX, now we are using MPI, and this MPI application can be scaled into a cluster system. So all of the, how you establish communication within the send receive, all of that is done for you internally MPI. So you don't have to worry about that. You just need to know how to use the MPI send and MPI receive function. Okay, that's how it works. And then if I want to exit, I enter -1, and then the programs all exit. That is how it works, exactly. I hope it gives you a very clear understanding. And in fact, many of you may think, hey, this looks much more easier. If you look at the p-thread signaling, it actually appears to be a bit more complicated. You have to use mutexes, you have to use condition variables, you have to use condition signal, condition wait, you have to use mutex lock and unlock. So at this glance, you must start thinking, hey, MPI now looks a bit more appealing in this context. All right, and actually it is. Although if you were to run this purely as a parallel program in a single computer, and you were to compare this with threads running multiple threads on a single computer, the threads will slightly be faster because MPI normally has more overheads when initializing, creating the communication rank and things like that. But in terms of its usage, it's far more easier. It's far more easier. But if you're doing pure parallel programming on shared memory, you shouldn't use MPI just because it's easy. If you're doing parallel programming on shared memory, you should still use either POSIX or OpenMP. But if you're doing parallel programming on distributed computing, distributed systems, where you're going to run a parallel program on a single computer, or you can scale it across multiple computers in the network, then this is how MPI actually works. Okay, so this is for send receive. So now I'm going to go a bit more quickly, because the question here asks you to use what? Ask you to use broadcast. The answer here says it's broadcast. Okay, the given answer here is broadcast. So this is point to point. Broadcast allows you to do collective communication. So in broadcast, rather than having the rank 0 call send and the other ranks, so we put if else. So rank 0 will only execute this chunk of the code. All other ranks in the process group will execute this chunk of the code. But all of them will do the do while loop. All right. Okay. Now, if I call MPI broadcast, you can see compare the code. You compare the code, is actually much more simpler now. I still do while loop. All processors will run this code, but only rank 0 prompts the value from the user. But you see, outside of the if statement now, I call MPI broadcast. So what is MPI broadcast? MPI broadcast is actually a collective communication of one to many. So the name applies, broadcast. So one of the processors will actually broadcast the value to all other processors within the group. All right. So if you go to the specifications, you search for MPI broadcast. Over here, you can find an MPI broadcast takes in the following arguments. Same thing, a pointer to a buffer or a value. How many elements in the buffer? What's the element type? Who is the broadcaster? Who is the broadcaster? And then after that, the communicator. So that is how MPI broadcast actually works. Okay, how it works, this is how it does. And MPI broadcast should be made visible to all processors. So if you look at the code over here, I'm not putting in MPI broadcast inside of the if statement my rank 0. No, you don't do this. It's wrong. MPI broadcast should be visible to everyone. So you can see there's no if statement inside here. So MPI broadcast will be executed by all processors, but rank 0 checks, oh, I am the broadcaster. So which means I am sending the content of this variable to everyone. All other ranks which are not 0 will see, oh, I'm the one supposed to receive it. So I will receive the value. So technically, if you were to compare this, MPI broadcast is actually internally, if you look internally, if you go into the open source version of MPI and look at the code inside there, you can find that MPI broadcast actually is a wrapper function to send and receive. It's a wrapper function to send and receive. That's about it, MPI broadcast. Okay, so that's MPI broadcast. So everyone now gets the variable. So if I run the program now, compile the code. Okay. So same thing. It works exactly the same behavior, but now rather than using send receive, we are using broadcast. I put another value. So the rank 0 broadcasts the value to all other processors in the communicator. -1, and then you'll exit. So give it a try. Give it a try, guys and girls. You'll find it very interesting. And you find it actually using MPI is actually a bit more easier than using threads. I mean, this is a matter of perspective. But again, that doesn't mean that you use MPI because it's easy. You use MPI because you use it based on the context. If you're doing it for parallel programming on distributed memory, you should use MPI. If you're doing parallel programming purely on shared memory, then you should use POSIX or OpenMP. Okay. So this is for question 2. So I hope you all can understand question 2 from now already. Now, question 3 is a bit tricky. Okay, question 3 says this. Now, let's say I want you to send multiple values. Okay, I want you to send out multiple values. All right, so let's say, okay, minute. Okay, let's say I want to send multiple values in the sense that, okay, let's modify this code. Now, look at the broadcast. Let's think. Okay, the question says, I want you to send a round number and a float and a real number. And a real number. So now I declare another variable over here. Let's say float. Float, let's say float value 2. Okay, value 2 equals to negative 1.0, something like that. Okay, example. So now I put scanf %d, and then I can put %lf. So now it reads two values, enter a round number and a real number. So I put it into address of value and then address of value 2. Example over here. Now, since you want to broadcast both values, so you have to do what? You have to repeat this word. You have to repeat this command twice. Now I broadcast second value. Because it's a float, I put here MPI underscore float. MPI underscore float. I put who's the broadcaster 0, and I broadcast to everyone within the communicator. So received round value. Received round value. I put this one here, and then after that, received received the round number. Received real number over here. So I put %lf. %lf, so value, and then I put here value 2. So this is what the question says. Question 3, you'll modify an argument to broadcast a routine to communicate different data types. Read an integer and a double precision. I mean, they ask you to double, but I'm using float here. Okay, never mind. Let's change it double. Double, because float is single precision. Float is single precision, but we can still use long. Okay, yeah. So I use double over here. Okay. MPI double. So the type is very important. If you're broadcasting an integer, you have to use integer. If you're broadcasting a double, you have to use double here. All right. MPI needs to know the type, because the MPI can calculate internally how many bytes are required to be transmitted and received. All right. Okay. So everything looks pretty good. Okay. Let's run the program. Okay. No errors. Okay, so it says enter a round number, a real number. So I enter a round number 9 and the real number. Let's say I put 6.5. So you can say here each process has received the value 9 and 6.5, and then enter a new one again. Let's say I put 8, and then let's say I put 87.5. Same thing, it works very well here. Okay, if I want to exit, I put -1 and I just put an arbitrary number. So now all the programs have exited, because -1 is our sentinel value to actually exit the entire loop over here. So this is simple. I mean, now you can broadcast two values. But that's not what the question wants. The question says what? Okay. The question didn't explicitly say, but they said using a single MPI broadcast call. A single MPI broadcast call, not double, not multiple. So the question says, now this is not fulfilling the question's requirement. If you were to submit this as a solution, it's not complete. It's not, I'm not saying it's complete, but not correct or inaccurate. It doesn't follow the question specification. The question says a MPI broadcast, not multiple MPI broadcasts. So how do you actually send multiple values within a single broadcast? That is what the third question is asking you to discuss. And that is where I'm going to introduce you to the next code over here, which is forwarded to you already. inside here. How we can actually, so there are two ways. Okay, so there are two ways. Oops, sorry. There are two ways on how we can broadcast multiple data types. Two ways. The first way is using create a custom data type. Create a custom MPI data type. And then the other method is by use packing and unpacking the data. Okay, two methods over here. You create a custom MPI data type and packing and unpacking. So question 3 is for the first one. Question 4, which we ask you to do on your own, is the second one. All right, so let me discuss with you all the first one. All right, okay. So how do you create a custom data type? So you can see it gets a bit more complex over here. So we started something very simple, send receive. We did broadcast, works even easier. You want to broadcast multiple values, fine, we call it MPI broadcast twice. But if you are required to use only broadcast once, but how do you send multiple values, different types of the values within a single broadcast? This is where we go into the next discussion. So what I'm doing now is I first created a structure, a C structure. So you need to be familiar with C structures. So C structures is actually similar to, I mean, if those of you all, I think many of you all have Java background. So in Java, when you call structures in C, a struct in C is more or less, I mean, just if you want to compare between structs and C in Java you have a class. Classes have variables which you can specify access specifiers, private, protected, public, and things like that. And then you have functions. Structs are there are a very small similarity in the sense that structs contains variables but don't contain functions. That's all. And the variables are all public by default. There's no private or protected in struct variables. And then you can instantiate an object to a struct. Okay, in C you have to call a struct and then a struct name and the struct variable. And then you can use the dot operator to access the variables. So the usage is similar to Java, just that you use dot operator. Okay, but just that structs only contain variables. So over here, I've created a structure to store an integer and a double precision value. I instantiate a variable of type struct, just like in Java, how you would instantiate a variable of type class. Okay. Then after that, so these are some new variables. So this is something I would like everyone to do some self-study. We have given you the code. Okay, so this may appear a bit new to you all. That's why we are making this a bit guided exercise. So we hope that you all can do some self-study and discuss your tutors exactly how each of these components actually work, but I will go through with you all. Okay, I then declare a MPI data type. So MPI data type is just, if you search online for MPI data type, okay, MPI, so you specify MPI data type. It's an enumerator. It's an enumerator, okay, but you specify a variable of the type enumerator, okay. Then you specify another array of the type MPI data type, 2 elements, and you specify integer and double. So why integer and double? Because this data type matches the number of elements inside, the number of types inside here. So I have 1 integer, I have 1 double. So just bear in mind, just follow my guidelines first. I know you'll be thinking what's going on here. This is all new to me, okay? But once you go through this and then you do a bit more of self-reading, you'll get the hang of it. And then I declare an array, integer array of 2, block length. And then I put 1, 1 here. So why 1, 1? Why 1, 1? Because how many elements are there in this structure? How many elements? Not how many bytes, how many elements? 2 elements, integer A, double B. So The first element, the first type is single element. The second type is single element. Should it be an array? Let's say double B10. Should it be an array example? Then this should be 10. Okay. If it's okay, if it's, let's say I put here integer A5, then it should be what here? It should be 5. Okay. If let's say, oops, sorry. If let's say I put here char C, then it all changes. This becomes what? This becomes 3. This becomes MPI, char, and then this becomes what? 1. If I put another third element here. So the third element is how many count of that? 1. If I put char C10, then it becomes 10. So I hope you all understand this. Okay, this is how it works. All right. So, but now we are going to go back to the earlier one, only sending. Okay. Okay. So that's how it works over here. And then in MPI AINT is it's a variable type. It's a built-in MPI variable type that stores addresses. And I put here displacement 2. So it's an array of type MPI address that stores the address of each element in the struct. That's why I put 2. So the 2's here represents how many types of entities are there in the structure. Not how many elements per entity, but how many types of entities are there in the structure. So if I have 3 entities in the structure, 3. If I have 2, 2. The number of elements per each entity are, you put it inside the block length over here. All right, so just bear with me for a while. Then after that, we do MPI init, MPI comrank. Then this is new. I call MPI get address. So MPI get address, if you search in the specifications over here, MPI get address, I pass in the address of the structure of the object. This object is of type structure value struct. I pass in the address of the object dot A, which means the address of this variable inside this, the address of this entity in this struct variable. And then I get the address. So MPI get address will get the address of this variable and store it inside this array content. Same thing it does it for B. Same thing does it for B. So I know it looks complicated. All right. So don't get discouraged. All right. We are all learning inside here. So once you get the idea, some practice, you will only get better. You won't. All right. So the practice will make it better and better for you. Then now we have to make it relative. So because the displacement here shows how much, what is the offset? We are trying to calculate how many bytes are actually offset. How many bytes B is from A. So in the memory, okay, in your memory, so you have your variable A and variable B. Actually, your variable A will take 4 bytes. It's an integer. And your variable B is a double, will take 8 bytes. All right. So what we want to do, we want to get the address of A inside here and store it in this array, displacement, MPI address. And then the address of B and store it at the second element inside this displacement. And then we want to calculate the offset. So displacement 0 will always be 0. The position, this is the position 0. Displacement and location 1 is the offset. So we take the address. We take the starting address here, the address here, minus the address over here. So this will tell me is 4 bytes. So this will, displacement 1 will always give 4 bytes in this example over here. So which means after line 27, displacement 0 will contain displacement 0 will contain 0, 0, of course. Okay. And displacement 1 will contain 4. Because how many bytes offset to here? All right, that's how it works. So based on all of this information, now we create our custom data type. We create a custom data type as a MPI type create struct. Now you'll be wondering, why can't I just send the struct? No, we can't. The MPI data type, you can see over here, as I shown you over here, the MPI data type specifies all of the known data types. So when you call MPI broadcast, you can put MPI long, MPI integer data type. But there's no struct because the struct is custom. As a programmer, you can specify whatever entities you want in a struct. So because of that, if you want to send multiple elements in one broadcast, you have to create a custom data type as a structure. That's why we call MPI type create struct. MPI type create struct, if you go to the specifications over here, you click this one. So you can see it takes in a series of arguments. Okay, let me go through with that, y'all. All right, the first argument is how many elements are there in your structure. So two elements. The second element is what is the block length. So this is the block length just now, remember? How many elements are there? So they want an array that shows what is the number of elements per each entity. So in this case, it's simple, one element. So you pass in the block length inside here. The third argument is important. They want to know the displacement. How many bytes are displaced between each entity? That's why we did the displacement. We get the address and then we compute the displacement. So you pass in the displacement array inside here. And then the type here just now, what is the type of each element entity in the structure? So I pass in the array type inside here, integer double. And then finally, all of these are input, and then MPI create struct will create a custom type, which is then written as an output argument over here. Okay, it is written as an output argument over here, and then you commit to it. You have to commit this data type. If you don't commit, it cannot be used. Once you have done that, the rest of it is easy. This is exactly the same. You prompt the user for a value. You get the values now into the struct. Okay, into the struct, and then I broadcast. I now can send a structure. You see, compare this to the earlier example. Rather than calling MPI broadcast twice, I only call MPI broadcast once. I pass in the address of my structure object, number of values 2. Now, last time in the previous example, I specify MPI integer for the first value, round, MPI double second value. Now I specify my custom created MPI data type. And then who's the broadcaster? 0 and convol, and then everyone gets it. That's it. I mean, at first glance, it looks, wow, this is complicated. But actually, guys and girls, it's not. When you understand it, you understand what they require, and you follow it, it becomes doable. So, but nevertheless, I fully understand that if you're finding it a bit hard to follow, get the gist of it. You can rewind back the video and see and repeat again so you can get the idea. So again, all right. The value type is your custom created value type. Then you specify an array of the type of elements in your structure. Specify another integer array, how many elements per each entity. Okay. And then the displacement to show the offset between the number of bytes for each entity. And then you call get address to get the address and compute the offsets. And then you call create struct. You pass in all the arguments inside here, and then it will create for you your custom data type of this structure. And then now you can call MPI broadcast using this. That is how it works. And then if I compile a code, it will work just the same. It will work just the same. I'm going to change this to type struct. Okay. And then I run it. Same. 9.6. It works just the same. 50, 98.5. It works just the same. Okay. Just that now, instead of having to call broadcast multiple times, you call broadcast only once. Now you'll be arguing, what's the point? Why do I want to go through all the headache of having to do this when I just call multiple broadcast twice? I mean, why is the tutors, why is the lecturer making my life miserable by by asking y'all, by asking me to do this, by asking, I mean, yeah, I'm learning something new, but isn't this much more easier? Now, bear in mind, every time you call an MPI communication function, whether it's broadcast, send, receive, there are always overheads. You have to establish a communication with the recipients. So if you call broadcast multiple times, the overheads increases. But if you call broadcast once, you minimize the overheads. So actually, in a way, you are actually improving the performance of your overall parallel computation time. So that's the benefit there of using MPI broadcast. All right. That's the benefit of using MPI create struct to create a custom type to send multiple elements of different entities in a single broadcast. So this is one method. This is one method in question 3. The second method, which is where we ask you to do it as your own exercise now. So this is the ones where you need to actually complete and submit as part of your lab assessment. Okay, is to use MPI, pack, unpack, and broadcast. So I'm not going to go in detail into this because this is something that we employ you all to try and see. But having said that, we did provide you a sample code on MPI, pack, and unpack. Similar problem. Not for a similar problem. It's for a different problem because similar problem I'm giving the answers then already. Okay, but it's a different problem. But you can see, please go through, please do some self-study. So MPI pack and unpack is a different approach on how you can call MPI send once, but this time you pack different types of data into a single buffer. You pack different types of data, I'm repeating again, sorry, into a single buffer, and then you send that buffer once. And then when you receive it, you unpack it, and then you print out the value. So this is the sample code that is provided to you all. Okay, this is the second method I refer to you all, and this is required for you all in question 4 for you all to do on your own. So please go through them. Okay, once you understand this first one, creating a custom MPI data type, the second one should be fairly easy. All right, so you call MPI receive, you call MPI pack, MPI unpack. So you can always find information in the open MPI specifications for MPI pack. So I've given you a code. We're giving you a code here to look at MPI pack and MPI unpack, how it works. You can find some online examples on how to use MPI pack and MPI unpack. There's a lot of online examples. And you can see how they can combine different types of data. In this case, it's an integer and a char array into a single buffer. And then they send the buffer into a single buffer, and then they send the buffer to the recipient. So take note of the position as the offset controller. All right, so please do some self-study here, and I hope this will help you all with question 4. This example. All of this code will be provided to you all in the pre-lab section in the video description. All right. And the last one, the last question is based on a problem to parallelize a serial code. We're giving you a serial code using MPI to parallelize the serial code on calculating pi. On approximating pi. Okay, this particular example, we like to use reduce. So what is reduce? So we're giving you another example over here. Now, reduce is it's a reduction operation. So if you, okay, so it allows you to so in this example over here, okay. So let's say I got process 0, process 1, process 2, all the way to process 7. So let's say I have a number 10, 11, 12, 13, and I want to sum them up into a global, into a common variable, which can be then captured by one process. So this is where you can use reduce. So you want to reduce the variables based on the reduction operation into a common variable over here. That is where we are using MPI reduce. So as you can see over here, each process will have their own local value. So my rank plus 1. The global value is 0. MPI reduce takes the local value and reduces it into the global value based on the reduction operation over here. What kind of reduction operation? So you can search up MPI reduce. Okay, there's an example over here, very good example. Okay, maybe another one. I think yeah, this is a good example in MPI tutorial. MPI reduce. It reduces the values into a common variable which can be captured by the root in this case. So there are many types of reduction you can do. You can find a maximum, minimum, sum, product, and you also can do some logical operations also. All right. So in this case, I want to call MPI. I want to reduce all the local variables, sum them up and store into the global value. MPI reduce. Okay. And so if you look at the function MPI reduce, what it does here. So let's go to, let's search for the specifications over here. Okay, reduces all values within a group. So it takes in what? The local variable, the variable to reduce into, the data type, what is the operation, who is the root? Who is the root here? So in this case, I'm specifying, I can put any processor to be the root. So let's say I put process 0 to be the root. Process 0 to be the root, and then communicator over here. And then you print out the values here. So you can see, if I were to run this code now, okay, I got warning, unused variables, tag and end. Okay, maybe you don't need this. Let me go back again. Okay. Now, if I have to run the MPI run, so it shows that all the each rank had the local value. Rank 0 local value is 1, rank 1 local value is 2, rank 3 local value is 4, and so forth. But you can see all of them will call MPI reduce, but only rank 0 keeps the global value. All the other ranks do not have the global value. All of them is 0. Only rank 0 keeps it because I put here 0. Okay, let's say if I put another processor, let's say I want the last process to collect the sum of them. Then now you can see the last rank 0's global value is 0. The last one is 5 as the value. If you want all the processors to have the reduced value, then you can use MPI all reduce. So this one you can give it a try on your own. So all of this code will be provided to you all. Based on all of this information, we hope that you should now be able to complete the lab exercise faithfully with your respective team members. Okay, please go through the code. Please go through you can go through the video again to get a better idea. For MPI pack, okay, do some self-study on how MPI pack actually works. It will really give you a better understanding. And then you have, now after this, you have different options on how you can use one MPI send or one MPI broadcast to broadcast multiple values. Okay, in my past, some students like using MPI pack, some students like using MPI create struct. They are both different approaches, but with the same objective of allowing you to send different types of entities within a single broadcast or single send and receive. Okay, and finally, before I conclude this video, at the beginning, they actually asked you to try out using makefile. So what is makefile? So far you are using GCC, MPI-CC. What is makefile? Typically, we have, Linux systems, you can actually use the make command to actually compile multiple files. So if you create a makefile, you have to be the same file format here. Okay, if you have a makefile, if you create a makefile over here, I will provide this makefile to you all. Okay, and there's no extension here, just the same name, capital M-A-K-E-F-I-L-E. And if you open this file, sorry, maybe I should open it with, okay. So inside here, we can specify targets. These are all the targets. So you can specify make all, and then you can specify custom target. So let's say I put make all over here, and then I put colon, And then let's say I want to compile 3 files. So I put my P thread signal, my MPI send receive, my MPI broadcast. And then in these are my targets, sub targets. And then you can see over here, my P thread signal, my MPI send receive, and my MPI broadcast over here. And then in this target, I specify the files required. So I can put multiple files, just put a space bar over here. You can put multiple files. And then you specify the compiling command, GCC, for this target, this command, this target, this command over here. And then I can specify the run target. The run target then will execute all of these applications. And then the clean target will then clean this code. So once I created this makefile, so provided you have all the code files created here already, then it's very easy. So you can see over here, okay, I'm going to now clear everything. So now I just call make. I use the make. So the make is a built-in command in Linux system. So I call make. Let's say I use make all. So make all will look for this makefile. This makefile doesn't exist, it will show an error. Okay, it will look for the open this makefile, and then it will look for the first target, make all. So it will compile all 3 of the sub targets over here. So you can see it's compiling all 3 files. It will create 3 different output files. I put 3 different output files over here. As you can see, it's created 3 different output files. Okay. Then if I want to run the program, I just do make run. So make run will then run all 3 programs, but you will run it sequentially. So you run the first, oops, my bad, here. Make run. So you will run the first program, then the second program, okay, and then the third program. The third program, you will run them all together. All right, that's how we can use make. So make is a very useful file if you are doing multiple, if you're creating multiple code files. You can actually use make here. It's very convenient. And then if you want to clean the files later on, you just call. Sorry, let me delete this program. Oops, I think something has happened. Oh, and the real number. Yeah, okay, exited. Sorry. Okay. Call make clean. Make clean, you will run the clean target, and then you will clean up all of the files, output files specified over here. So yeah, that's it for makefile. You can I mean, it's not compulsory for you all to use makefile in this unit, but we strongly encourage you all to use it. At least it will give you a better exposure on how to do a more comprehensive C program development for this unit. Okay. So that's all. So we have covered I showed you how to transition from thread-based parallelism to process-based parallelism. Okay, how we did the examples from p-thread signaling, and then we went to how we can achieve that using process-based parallelism using MPI, and then how we can use quality communication with MPI broadcast, and how we can use type struct to send multiple values within a single broadcast. And then I've given you a very brief overview of MPI pack and unpack because it's part of your assessment. And then I've given you a walkthrough MPI reduce, which you will need to use when solving the final question for your lab assessment. Okay, so I hope all this video is useful. I'll try to provide the annotation, I mean the labels in the video, so you can know which time to skip to go to that particular section to review the topics, the subtopics discussed in this video. Okay, so that's about it. Thank you very much, and I will see you all again soon. Take care.